Hello students, welcome back to your favorite YouTube channel, Tomachang Tutorial. Myself Kishan Kulum, and today we are going to discuss about a new chapter in physics called thermal expansion. Okay, we will discuss about thermal expansion in this video, but before going in depth of the chapter, let us understand what heat and temperature is. Let's understand this first. Definition of heat. It is the form of energy by the application of which the body becomes hot and by the extraction of which the body becomes cold. Okay. Heat is just a form of energy like light energy. Light energy is also a form of energy. Electrical energy, magnetic energy, wind energy. Okay. Heat is also a form of energy. And by the application of heat, the body becomes hot, which means when a body absorbs heat, the body becomes hot. And when a body loses heat, the body becomes cold. Okay? When body loses heat or when heat is extracted from the body becomes cold. Very, very simple. I'll give an example. Okay? Take amount of water, put that water on top of a gas oven and heat for some time. After some time, you see that water has already become hot, isn't it? That's very, very simple. When water absorbs heat from the gas oven, the water becomes hot. If we put that same water into the fridge, the refrigerator, okay? When we put water into the refrigerator, what does the refrigerator do? The refrigerator extracts heat from the water. And when heat is extracted from the water becomes cold, and after some time it freezes, isn't it? So when heat is applied on a body, the body becomes hot, and when heat is extracted from the body becomes cold. That's all. Very simple, isn't it? Now let's see the unit of heat. SI unit of heat is joule, 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 and its symbol is capital letter J. Okay, and the CGS unit of heat is calorie. Okay, CAL, calorie. Okay, temperature. Now let's come to the point. Temperature actually it is the condition of the body. It is the thermal condition of the body. Now let's say this is a body. When I touch this body, if I feel hot, then we say the temperature of this body is high. And when I touch this body, if I feel cold, then we say the temperature of this body is low. Temperature is just a thermal condition which determines whether the body is hot or the body is cold. Temperature is just the thermal condition of the body. It determines the hotness or coldness of the body. When we touch the body, if the temperature is high, the body will be obviously hot. If the temperature of the body is low, the body is at low temperature. Okay, I hope you got this point. Now, the SI unit of temperature is Kelvin. It's denoted by the letter capital K. Okay, and the CGS unit of temperature is degree Celsius and is denoted by degree Celsius, like this. Many students, they make mistake and write degree in Kelvin. Please remember, degree should not be put here in Kelvin. Kelvin is just K, okay? Do not put degree like in degree Celsius. Okay, now let us understand about the principle of flow of heat. We will definitely discuss about the topic in thermal conduction of heat, but now as an introductory, I am going to give you the idea of flow of heat. From which body the heat flows to which body, okay? Let me draw two cylinders connected by a pipe. These are two cylinders, okay? These are two cylinders and this two cylinder is connected by a pipe. And this cylinder contains water, okay? Water is in this cylinder. Let us say this is cylinder A and this is cylinder B, okay? Looking at this cylinder, two cylinders, if you are asked to guess which cylinder contains more amount of water, you would obviously say the cylinder B contains more amount of water, isn't it, compared to cylinder A, because cylinder B has greater amount of water, the size of cylinder B is more, so it contains greater amount of water. So cylinder B has greater amount of water. But if I ask you from which cylinder to which cylinder the water flows, the direction of water will be from which cylinder to which cylinder, because cylinder B contains greater amount of water and cylinder A contains lesser amount of water, but the level of water in cylinder A is at higher level and the level of water in cylinder B is at lower level, isn't it? Now, if I ask you from which cylinder to which cylinder the flow of water takes place, then the answer will be the water will flow from cylinder A to cylinder B. Please understand, though the quantity of water in cylinder B is much more than the quantity of water in cylinder A, even then water will flow from cylinder A to cylinder B because the level of water in cylinder A is higher than the level of water in cylinder B. The similar concept will be applied in the process of flow of heat also. Let me give you an example, okay? These are two bodies. Okay, these are two bodies. Let me consider this is body A and this is body B. Let us assume this body has 20 calories of heat, okay? This body has 20 calories of heat. The heat energy in this body is 20 calories and the heat energy in this body is 2 calories only. The temperature of this body is 5 degrees Celsius. I am just assuming it. The temperature of this body is 2 degrees Celsius. 20 degrees Celsius, okay? Now, if we somehow connect these two bodies, if we bring these two bodies in contact with each other, then from which body the heat will flow to which body? I mean, the heat will flow from body A to body B, or the heat will flow from body B to body A. The question is, from which body to which body the heat will flow? The answer is very, very simple. Similar to the case of water, though the amount of heat energy in body A is much higher than the amount of heat in body B. In body A, we can see 20 calories of heat, which is much more than 2 calories of heat, isn't it? Even then, heat will flow from body B to body A because the temperature of the body B is higher than the temperature of body A. Which means, similar to the concept of water, the level of water determines the flow of water. Here, the level of temperature determines the flow of heat. If the body is at higher temperature, then the body loses heat. If the body is at lower temperature, then the body gains heat. The body at higher temperature, when comes in contact with the body with lower temperature, loses heat. The body with lower temperature, when comes in contact with the body with higher temperature, gains heat. Okay, got my point? Okay, we understood about heat and temperature. Now we will move on to our main topic, that is thermal expansion. Okay, thermal expansion of solid, thermal expansion of liquid, and thermal expansion of gas. All three states of matter, solid, liquid and gas, expands on heating. Okay, we will understand about the thermal expansion of thermal expansion of liquid and gas in our later videos, but right now we will begin from the thermal expansion of solids. Let's begin. Expansion of solids on heating. Every solids on heating expands, okay? Every solids on heating expands, but remember, metals expands more than non-metals. Got it? Metals expands more than non-metals, but every solids expands on heating to some extent. Okay, let me give you an example. We must have seen a small gap is maintained between the two rail lines, isn't it? A small gap is maintained between the two rail lines. The question is, why is this gap maintained? Or what is the purpose of this gap between the two rail lines? And the answer is, during the hot summer days when the heat of the sun is very high, the heat of the sun is very much, and when train runs over this rail line, the wheels of the train, you know, it's made out of iron. The friction between the wheels of the train and the rail line causes the generation of heat. That heat energy in turn expands the rail line because metal expands on heating. The heat energy generated by the friction between the rail line and the wheels of the train expands the rail line, okay? And when there is a gap left, this expanded rail lines fills up this gap. Got my point? The expanded rail lines fills up this gap, okay? And when the train passes by, after some time, this rail line cools down again. And when the rail line cools down again, the gap is again maintained, okay? I hope you got this. Now, suppose if no gap is left in between the two rail lines, if the rail lines is made in this way, keeping no gap like this, okay? If the rail lines are made in this way, what would happen? When the train runs over this rail line, the friction of the wheel and the rail line causes heat to generate, and that heat energy causes the expansion of this rail line, but there is no space for expansion of the rail line, so this rail line would bend in this way, isn't it? Are you getting my point? Though my drawing is not so good, but I am very sure you understood this. The rail line would bend in this way and the chances of derailment would occur. To avoid the accident of the train, to avoid derailment of the train, this gap is always maintained between the two rail lines, okay? I hope you understood this. Let us understand the expansion of solid by another example. This is actually an experiment, okay? A metallic ball is suspended by a thread and there is a ring, okay? And this ring is not so big enough that the ball can easily pass up and down. Got my point? This ring is just a little bit bigger the size of this ball so that the ball can fit through the ring at the room temperature. Remember, at the room temperature, okay? The ball can just pass through the ring at the room temperature. Got my point? Now, let us see what happens when we hit the ball, okay? When we hit the ball. See, when you hit the ball, you will find or you will see that the ball will no longer pass through the ring. The ball will no longer pass through the ring, which means the size of the ball has increased. The heat energy causes the expansion of the ball, the thermal expansion of the ball. Got my point? When you hit the ball increases in size. The volume of the ball increases, so now the ball cannot pass through the ring. Got my point? Now, let us remove the heat and let the ball cool for some time. When the ball cools down again, the ball will be able to pass through the ring again, okay? Now, this experiment clearly proves that metals or the solids, metals, especially metals, okay? Metals on heating expands and on cooling contracts. When you heat metal, the metal expands, and when you cool metal, the metal contracts. This experiment shows that. Okay, I hope you got this. Now, the question is, do all the metals expands equally for equal amount of heat? Do you get my question? Do all the metals expands equally for equal amount of heat for equal rise of temperature? Let's see. This is a bimetallic stripe, okay? This is a bimetallic stripe. Bimetallic stripe. Bimetallic means made out of two metals, okay? This is suppose iron and this is brass. This bimetallic stripe is made out of iron and brass. This is iron and this is brass, okay? So the bimetallic stripe, you can see it is straight. Now let us hit this bimetallic stripe and see what happens to it. When you hit this bimetallic stripe, you will see the bimetallic stripe is found to bend like this, okay? The bimetallic stripe is found to bend like this. And you will see that the brass remains on the convex side and the iron remains on the concave side, okay? You will see that the brass is on the convex side of the bimetallic stripe and the iron is on the concave side. Iron and this is brass. Got my point? The first question is if the metals on heating expands equally, if all the metals expands equally on heating, then this bimetallic stripe when heated equally would have remained straight as before, isn't it? Because equal amount of heat is given to both the metals iron and brass. So if this iron and brass would expand equally for equal amount of heat or the equal rise of temperature, then these two metals would expand equally, then this bimetallic stripe would remain straight as before. But this bimetallic stripe is seen to bend in this way, which means these metals did not expand equally. Got my point? This bimetallic stripe shows that brass and iron expanded unequally for the equal amount of heat, isn't it? And moreover, we saw that brass is on the convex side, which means brass expanded more than iron for same amount of heat, and iron expanded less than brass for the same amount of heat, isn't it? Okay, now let me give you a table to make you understand more. Okay, let me erase this. Suppose we write metals here and we write coefficient of linear expansion in CGS unit, okay? In CGS unit. Got my point? I'm writing this in CGS unit. If the metal is iron, the coefficient of linear expansion of iron in CGS unit is 1.2 into 10 to the power minus 5 per degree Celsius rise in temperature. If the metal is steel, then the coefficient of linear expansion is 1.1 into 10 to the power minus 5 per degree Celsius rise in temperature. If the metal is brass, then the coefficient of linear expansion will be 1.9 into 10 to the power minus 5 per degree Celsius rise in temperature. And if the metal is copper, then the coefficient of linear expansion will be 1.7 into 10 to the power minus 5 per degree Celsius rise in temperature. This is just an example to show you, okay, this is a table. From here you can see the coefficient of linear expansion of iron is 1.2 into 10 to the power minus 5 per degree Celsius rise in temperature, and the coefficient of brass is 1.9 into 10 to the power minus 5 per degree Celsius rise in temperature, isn't it? Now among this 1.2 and 1.9, because the rest are same, 1.2 and 1.9, which number is greater? Obviously 1.9 is greater, right? So brass expands more than iron, okay? Brass remains, or brass is in the convex side because the coefficient of linear expansion of brass is more than that of iron. Okay, this table shows us, and this experiment shows us, that all metals do not expand equally for equal amount of heat or equal rise of temperature, okay?